Hey folks, Mr. Nickel here. We're going to talk about one of my favorite topics today, which is organic chemistry. We're going to introduce some of the basic concepts of it, talk about how we represent molecules when it comes to organic chemistry, as well as talk about some hydrocarbons, some alkanes, alkenes, and alkynes. And I'm really looking forward to this unit because I absolutely love this unit. So, some things that we need to talk about first. When we talk about organic chemistry, when we talk about organic molecules, we are not talking about food items that have been grown without the use of pesticides, herbicides. Instead, what we're talking about is anytime we mention something as an organic compound, generally it's only made of a few elements. It's made of carbons, hydrogens, and then also sometimes oxygens and nitrogens as well. But the two main backbones of organic molecules is carbons and hydrogens. And so the first thing we're going to talk about is just what a hydrocarbon is. A hydrocarbon is anything that's made of only hydrogens and carbons. As soon as we start adding other elements in, it no longer becomes a hydrocarbon. Now, something I want to get out of the way before we get into this unit, there will be a lot of cases throughout this entire unit where you see something called the R group. So you'll have some carbon, it'll be bonded to, I don't know, let's say a couple different hydrogens. And then you'll see this R group. Now, it's worth noting there's no R on the periodic table. Instead, what this R is saying is that it can be any number of or length of carbons. And the idea is saying that it's sort of anything else that goes over on this side of the molecule. It's not saying it has to specifically be this many carbons, this many nitrogens, etc. It's basically saying, like, it doesn't really matter what's over here. We're only focusing on this. And so the R group is sort of like the, I don't know, there's stuff over here. It's like the etc. of chemistry. So we have a couple different functional groups that we're going to talk about. Now, a functional group, I'm going to use that term quite a bit, functional group. Functional group. What a functional group is, as you can imagine, it determines the function or the purpose of a molecule. Now, functional groups, when we look at them, have a specific design to them. There's going to be a specific arrangement of atoms within the grand schema of the molecule, and based on those, we'll change the name of the functional group. So the whole purpose of what we're doing organic chemistry with is to adjust the names and come up with more formal names for bigger molecules, but also for us to be able to predict, what the function of each of these molecules might be based on the functional groups that are present. So if we have an alkane, we're going to have something where we have all carbons within a chain of a molecule single bonded to each other. And here I'm going to use that R group because it doesn't really matter what's beside. Use that R group again beside here. So what we're going to have is all of our carbons will be single bonded to one another. Anytime we have an alkene, what that simply means is this is our first example of a functional group. It means that somewhere in the molecule, there will be a carbon double bonded to another carbon. And you'll also notice I'm doing something a little different here. Notice that I'm only giving carbon 1, 2, 3, 4 bonds. So this carbon has 4 bonds around it, and this carbon also has 4 bonds around it. Reason being that carbon, being the backbone of everything, we need to memorize and know the fact that carbon has 4 valence electrons. So in other words, it'll want to make 4 bonds. Now that can be a double bond between something, it can be a triple bond between something, but ultimately we want to see 4 bonds coming off of our carbon. The last functional group that we're going to cover in this particular video is something called an alkyne. Now, an alkyne means that somewhere in the molecule, there's a carbon triple bonded to another carbon. Now, if you have a carbon and it's triple bonded to something else, like a nitrogen, for example, that is not an alkyne. An alkyne only is present when there's 2 carbons triple bonded to one another. In the same way that an alkene is only present when there's 2 carbons double bonded to each other. I'm going to use my R groups again here to show that it doesn't really matter what's on either side. It could be any string of carbons. It could just be another hydrogen. We're not totally sure. So carbon wants to always form 4 bonds, and that's because of its 4 singular valence electrons that it has around it. Now, when we get long chains of carbons, we want to be able to list and number well, how many consecutive carbons are there? So unfortunately, we're not going to use the same prefixes we used before with molecular compounds. When we were naming molecular compounds, we use mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Now, because we're talking about longer strings of molecules and not just how many carbons are there or how many oxygens are there, we're talking only about carbons. And so we're going to use these prefixes: meth, eth, prop, bute. It's not, but it's bute. Pent, hex, hept, oct, non, dec. So from pent down, those are the same, but meth, eth, prop, bute, those are the different ones. And so we have our numbers of carbons also listed there. Those will be an expectation that you be able to memorize those. Now, as far as drawing these molecules out, let's say that we wanted to draw propane and hexane, okay? So one of the things that we want to focus on, there's two different parts to these names. One is this first prop part, the P-R-O-P. That P-R-O-P is going to tell us that we are going to have 3 carbons. We're going to have 3 carbons in this molecule. The last part of the word, the ANE, this part here, if we go back up top here, is going to tell us that, well, if we have an alkane and we change the ending of the name to ANE, every single carbon and hydrogen is going to be single bonded. Now you'll notice I have 2 regions for this. I'm going to show you the 2 different ways that you can draw this. So propane, we have 1, 2, 3 different carbons. And what we need to do is make sure that each of those have 4 bonds coming off of them. And anytime that we have, a space for a bond coming off of a carbon, we're going to fill it in with hydrogen. Since these are all organic molecules, they're all hydrocarbons. So what we have right now is we've established that 3 carbons because of prop. The ANE tells us that it's all single bonds. And so we have our molecule drawn here with our display formula. We have 3 carbons, all of them are single bonded. Now, if I were to do this for, like, let's say a nonane, a 9-carboned molecule, that would take me a very, very long time. And I don't want to do that. Chemists are notoriously lazy. And so what chemists came up with for drawing organic compounds is something called the skeletal formula, or the stick form. And the way that it works is you are going to draw that. And that is propane. We have, the way that these stick formulas work is that at each of these corners, so this corner, and this corner, we have a carbon represented there. If there is an element at a point, so let's say that we drew something like this, we would only have 1, 2 carbons on that molecule. And basically the way it works, again, at any point here, we're going to have a carbon atom. Now, these lines show us that, yes, this is a single bond between this carbon, and then we have a single bond between this carbon and this carbon. The other beauty of these is that we don't need to draw all of the hydrogens. We can just assume that they're there. So this carbon here, this one right here, only has 1 bond coming off of it. So what we would assume then is that there are 3 other hydrogens nearby. And so we don't need to show those hydrogens in that molecule, which is super nice for us. If we do hexane, so hexane, we have hex. Hex is the prefix for 6. So we're going to have 6 carbons. And then again, we have this ANE. So we're going to have all single bonded carbons. 1, 2, 3, 4, 5, 6 carbons. These 2 on the end will need 3 hydrogens beside them to fulfill carbon's desire for 4 bonds. And then each of the ones in the middle here will get 2 hydrogens. Now I'm sort of talking really slowly and sort of delaying the process of me drawing this because it takes an obnoxious amount of time for me to actually draw in all of those hydrogens. Instead, what I could do is I could do this. 1, 2, 3, 4, 5, 6. Both of those are hexanes, but the one on the right took me significantly less time to draw than the one on the left. So what we're going to start using is this skeletal formula, the stick form, for getting these structures drawn out. Now, with any sort of functional group or a compound or molecular compound, we're going to have a list of naming rules. And I've posted a document, and I'll make a video going through that document on the naming rule priority, where different functional groups that we're going to talk about will have a higher priority than other ones. But as far as our basic rules are concerned, these are what the rules are. We want to number the longest carbon chain possible so that the alkyls, so this would be an alkane or a alkene, or an alkyne. We want to make sure that those will have the absolute lowest number possible, and that'll make sense in a couple steps. The number that we're going to add is going to tell us where the functional groups will be added to the chain. Where we're going to number these functional groups to say, hey, that on this third carbon, there's this weird stick arm thingy coming off. And we're going to use letters and numbers to do that, but all letters and numbers need to be separated by a hyphen. If we have consecutive numbers, those will be separated by commas, and I'll show you that with this 3,3-dimethylheptane example. And then the functional groups that we have are named alphabetically. So if we have an ethyl group or a methyl group, we're going to name those alphabetically, not based on the number. That's sort of a confusing step. So we're going to look at this first molecule here. We've got this long stringed molecule right here. We see that there's a couple different directions that we can take this molecule. We could number this 1, 2, 3, and we'd have a 3-carbon molecule. But number 1 says that we want to number the longest chain so that the alkyl group will have the lowest number possible. So we know that we don't want to go 1, 2, and then down to this third one down here. Instead, I can make a longer chain if I go 1, 2, 3, 4, 5. So that's one option that I could do here. Well, I also have another option. I could start numbering from this end. 1, 2, 3, 4, 5. Both of those are 5 carbons long. Both of those will be a pentane. But one of them is going to be better. And the other one that's better is we want the alkyl group, so the alkane, alkene, or alkyne. Whatever arms or sticks we have coming off of this main carbon, it's called the parent chain, whatever we have coming off of the parent chain. We want that to have the lowest number possible. So I'm going to choose the 2, so 1, 2, instead of calling it carbon number 4. So we have our numbering up top there. We have carbons number 1, 2, 3, 4, and 5. So as far as naming this then, we want to say that this CH3 group here is coming off of carbon 2. And so the way that we're going to do that is we're going to say on carbon 2, and then we want to separate our numbers and letters with a hyphen. On carbon 2, we have a 1-carbon group coming off of that. And that 1-carbon group is a meth group. Because it's single bonded, we're going to call it a methyl group. And this YL comes from the fact that this is an alkyl group. Okay? So we have 2-methyl. And then what we want to describe is, well, okay, we've got this functional group, this 2-methyl described. Now we want to describe the main parent chain. And we can see that that main parent chain is 5 carbons long, which we know will be a pent. So we know that that carbon chain will be a pent. So this is because it's 5 carbons long. The next thing that we want to do is say, are there any double bonds anywhere in this molecule? And we can see we don't have any double bonds at all. So we can put the ending A and E in here to show that these are all single bonded. That's your first example of how to name a molecule. We just named this molecule up here. 2-methylpentane is the final name. Where it can get a bit confusing is when we need to go from the molecule to the name. I think going from the name to the molecule can slightly be the easier one because you have something to work off of. So what we're looking at here is we have 3,3-dimethylheptane. So looking at this here, I'm going to take a couple pieces of information. One, I'm going to say, okay, I've got a hept, so I know that I've got 7 carbons. And I have an A and E, so I know that those will all be single bonded to one another. Now what I've got here is I have a 3 and a 3. So I know that on the third carbon, I'm going to have some sort of functional group. And I can see that that functional group will be a methyl. This is the functional group. Now, what's interesting here is a word that we haven't yet encountered. We have this di here. I previously said that we won't use those Greek prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. The only time we use them is when there's more than one one of the same functional group. And so those were the mono, di, tri, tetra, penta. And you shouldn't ever have any more than penta, but it's hexa, hepta, octa, nona, deca beyond that point. If we have more than one methyl group, we describe it with a dimethyl. So this is telling me that on carbon 3 and on carbon 3, there are 2 methyl groups. So how I'm going to start this here, I'm going to do this one as a stick formula where I'm going to draw 7 different carbons. So 1, 2, 3, 4, 5, 6, and 7. And then I'll draw it down here as well. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So I have my 7 carbon chain. All of them are single bonded. So notice I haven't drawn any double bonds whatsoever on here. And then what we're going to do from there is on carbon 3 and carbon 3, we have 2 methyl groups. Now, the beauty of drawing your own molecule, carbon 3 can be whatever you want. I'm going to call this one carbon 3. And I'm going to call this one carbon 3 over here. If I want to draw a dimethyl group, a methyl group is 1 additional carbon. Meth stands for 1. So we're going to draw 1 additional carbon. And then I'm drawing H3 because we know that each carbon wants to have 4 different bonds made with it. So this carbon has this 1 bond to the main parent chain here. And then we know that it'll need 3 additional H's. Yes, you can draw them around the carbon, but I don't think it's super necessary to do so in this case. Lots of fun little tricks. And I'm showing you these different things too because as you're Googling and researching stuff in the class, you'll see all of these different variations on Google. And I want you to be familiar that, yeah, there's like 3 or 4 or 5 or 6 different ways that you can represent the same molecule. All of them are correct. If we wanted to do our 2 methyl groups, our dimethyl group on the stick formula, we draw 1 stick here and we draw 1 stick here. So then we have 1, 2, 3, a methyl here, a CH3, and a CH3 here. So that's how you'd get that molecule down there. Now we're going to do one last one, and I love this particular example because this example is awesome for the numbering of this CH3. We have a couple different opportunities here. We could name this as a 1, 2, 3 carbon, but what we're doing is we are missing a whole chunk of information over here, and we'd miss all of that with our name. It's also not the longest chain that we can have. We could have a 1, 2, 3, 4, 5, 6 carbon chain. Again, I think we can do better. I think we can make it longer than that. We could have a 1, 2, 3, 4, 5, 6, 7. Well, that's a 7 carbon chain. That's longer than 6. I like this one so far. But the second part of that rule number 1 was that we wanted to have any functional groups. So in this case, our functional groups will be this one and this one. We wanted those to have the lowest number possible. And right now I have a number 4. So on carbon 4, we have this functional group coming off. And carbon 6, I have this functional group coming off. I can do better than that. If I start numbering this one, I'm going to use red this time. If I can start numbering this one from here, we have 1, 2, 3, 4, 5, 6, 7. Now what we have is we have on carbon 2, a functional group, and on carbon 4, we have a functional group. So the information that we have here is we have a 7 carbon chain, so we know that that will be, if we go back up to the chart, a heptane. Okay, so we know that we have a hept. We have all single bonds, so we know that this will be an ANE ending for us. And then we have 2 different functional groups here. We have a CH3, which is going to be a methyl group. And then we have a CH2CH3, so I'm going to write it like this, CH2CH3. That's a 2-carboned alkyl group. So in other words, that is a ethyl group. Okay, that's an ethyl group. And so if we go back up to our steps, what we want to do is we want to number our functional groups. Okay, we've done that already. And we want to separate our letters and numbers with the hyphen. We want consecutive numbers to be separated by commas. And then we want the functional groups to be named alphabetically. So we know that in this molecule, we are going to end the name of this with heptane, like this. We're going to end the name with HEPTANE. What we don't know is what goes in front of that. So for our options, we have a methyl group that is on carbon number 2. So I'm going to add a 2 to this. It's a 2 methyl group. And then the ethyl group is on number 4. We said that we wanted these to be listed alphabetically. So if I have an ethyl group here and a methyl group here, I want to list the ethyl group first. So I'm going to have 4 ethyl, separating my numbers and letters with hyphens, a 2 methyl, heptane. Now, notice that I haven't put a space, nor have I put a hyphen or a comma between methyl and heptane. And the reason is that those are all letters, and letters can be consecutive back to back to back. And so why I'm putting it as 2-methylheptane is because, again, I don't need to separate those two at all. We have all of our numbers separated by hyphens. We sorted this alphabetically. We had our 7 carbon ANE because they're all single bonded, and we identified that we had an ethyl group coming off of carbon 4 and a methyl group coming off of carbon 2. A little bit of a longer video. Hope this was a good introduction to organic chemistry. Hope this made sense to you. Let me know if you have any questions or comments at all, as always, and I hope you have an excellent rest of your day.